ready to start the last section of chapter 29. It's all about the magnetic properties of matter. This is pages 824 through 827 in your textbook. This part is not math heavy, it's just kind of interesting, and it answers the questions, why are magnets magnetic? So it's a pretty neat idea. So let's start by thinking about atoms. We're going to circle back around to the beginning of chapter 29. Moving charges make magnetic fields. And Ampere theorized that the molecular current loops are responsible for all magnetic phenomena. So we'll think about that idea a little bit. So consider any atom at all. Here's a sketch of one. Let's say that the electron moves around this way. If the electron is swirling around this way, that's a negative moving charge. It means that there's a current flowing around this way. Okay, so there's a current going around the nucleus. So our electron orbits. So every little atom has a current loop. Electron orbits, that's current. And current loops produce magnetic moments. And we know the direction of the magnetic moment. You curl your fingers in the direction of current, and your thumb shows your magnetic moment. So magnetic moment was the mu. So that means every single atom, because they all have spinning electrons, is a little tiny magnet, and each of them have a north and south pole. In many materials, those magnetic moments do tend to cancel. We're going to discuss that a bit on the next slide. But before we move on to that idea, let's talk about the electron itself. So the electron going around the nucleus is not the only motion. This little electron also spins. Okay, that's a little bit harder to discuss because electrons are so tiny, it's hard to say their motion, but we kind of infer that they have to be spinning. So a little rotating ball of charge is the same thing as a moving charge. So our little rotating ball of charge makes a magnetic field or a magnetic moment. So our electron going around the nucleus produces a magnetic moment, and the electron spinning around by itself also makes a magnetic moment. Now we know that in most atoms all the electrons are paired. It's probably something you studied in a chemistry class. But if we say most of them are paired, and that means that the moments cancel, it means that not all of them are paired. So some of them are unpaired. And the unpaired ones have a magnetic moment which contribute to the magnetic field of the overall material. So that's a pretty interesting idea, and that brings us to permanent magnets. So what we have on the left is the picture of an unmagnetic material. So this is just most materials, because most things are not magnetic. In most of our materials, the unpaired electrons, so everything has some unpaired electrons, but in most materials, those unpaired electrons spin in random directions. So unpaired electrons, they spin or they point in random directions. That means that the net magnetic moment is the sum of all those individual magnetic moments. They sum up to be 0. So all those moments cancel. The net magnetic moment equals 0. So that's most of your things. Those are the things that are not magnetic. But we do have some things that are magnetic. Those are called ferromagnetic. Ferromagnetic materials are different. The prefix ferro, it means iron. because this idea applies to iron, which was probably the first magnetic material studied. So anything that's magnetic we call ferromagnetic because it's like iron. In ferromagnetic materials, all of these unpaired electrons, they line up. So all of the magnetic moments are aligned. Okay, so north and a south pole. That results in a net magnetic moment. So mu net is not zero. So that's kind of cool. When you stick a magnet on your fridge, you're actually seeing the effect of the little electrons in the material that are spinning. So that's kind of a cool idea. Let's just kind of discuss this a tiny bit more. Most materials, magnetic materials, so we'll stick with the ferromagnetism for right now, most materials aren't perfectly aligned like this. Most of them just have little bits that are aligned like this. So most magnetic materials have areas where things are all lined up, and those little areas are called domains. So each domain has a magnetic moment. One of the things that's kind of neat about that is you can change the magnetic moment of a domain pretty simply. If you drop a permanent magnet often enough, you will actually cause all these guys to scatter. So every time you drop it, you will bump those. If you drop it often enough, you'll knock them all out of alignment and they won't be magnetized anymore. It's why you have to be so careful with a compass. If you drop a compass one too many times, it will lose its magnetic field inside the magnet itself. On the flip side, you can also increase the magnetism of an object by inducing more alignment. So you lose the magnetism if you knock them out of line. You'll increase the magnetism if you put them in line. And that's in fact how an electromagnet works. So if you take a solenoid, that's our coils of wire. If you take a solenoid, we know it makes a big magnetic field that's strong and it's constant. And if you bring that field close to a ferromagnetic material, it will cause all those little electrons to line up with that magnetic field. So that will overall magnetize the material. So when we put our galvanized nail inside this electromagnet, it turns into a magnet because the solenoid's magnetic field causes all the little electrons, all their little magnetic moments to line up. So that's what turns it into a magnet. Okay, in the next video we're going to start chapter 30, which is all about induced EMF and induced currents. Really interesting stuff.